Everyone who watches Yellowstone expects the same warning sign: the ground rising. That's the image that's been burned into the public imagination. Swelling magma chambers, uplifting terrain, a slow volcanic breath inflating the land above it. That's the version of Yellowstone that fills documentaries and disaster films alike. So when satellites started returning, data showing a large section of the Yellowstone caldera region sinking, not swelling, but actively subsiding, over an area stretching more than 60 miles across, it created a very different kind of conversation among the people who study this system for a living. And that conversation is what I want to walk you through today. Not the panic version, not the "it's all going to blow" version. The actual version, what the satellite data captured, what the science says is likely driving it, and why the scale of this particular deformation event is genuinely worth understanding. Because the way Yellowstone actually behaves underground is far more interesting than the simplified story most people have heard. So what exactly did these satellite measurements pick up, and why are researchers paying close attention? The technology used to track ground deformation at Yellowstone and at volcanic systems around the world is called INSAR, which stands for Interferometric Synthetic Aperture Radar. The short version is this: satellites beam radar signals down to the Earth's surface, and by comparing multiple passes over the same area across time, researchers can detect vertical ground movement with remarkable precision, sometimes measuring changes of just a few millimeters. What showed up in recent measurement periods was a broad zone of subsidence, meaning the ground surface was measurably lower than previous readings, centered on and around the Yellowstone caldera, with the affected area extending significantly beyond the caldera boundary itself, reaching into surrounding terrain and covering that 60-plus mile footprint. Now, the word sinking conjures a very specific image that isn't quite accurate here. We're not talking about the ground suddenly dropping like a sinkhole. The rates of movement being measured are typically in the range of centimeters per year, sometimes even less. What makes it significant isn't the speed, it's the spatial scale, the pattern, and what it might be telling us about what's reorganizing beneath the surface. The USGS Yellowstone Volcano Observatory, which maintains one of the most comprehensive volcanic monitoring networks in the world, regularly publishes deformation data from GPS stations and satellite observations. This most recent pattern of subsidence fits within a broader history of oscillating behavior at this site, but the geographic reach of this particular episode has drawn focused attention from researchers tracking how the system evolves. To understand what's happening beneath that 60-mile zone, you have to understand something about how Yellowstone actually works as a system, because it's not the simple, giant magma chamber waiting to explode picture that tends to dominate the coverage. Yellowstone sits above what geologists call a hot spot, a plume of abnormally hot mantle material rising from deep within the Earth. That heat source powers the geothermal activity you see at the surface. The geysers, the hot springs, the mud pots, all of it. But it also feeds a complex plumbing system that includes not just magma, but vast reservoirs of superheated water and gases that permeate the rock beneath the park. The ground at Yellowstone rises and falls for multiple reasons, and distinguishing between them is a significant part of what volcanologists and geodesists work on. Uplift, the ground rising, can mean magma is moving upward and accumulating closer to the surface. It can also mean hydrothermal fluids are expanding, or that water is being drawn into the hydrothermal system faster than it's being released. Subsidence, the ground sinking, is essentially the inverse. It can indicate that fluids are migrating deeper or draining out of a subsurface reservoir. It can reflect the slow cooling and contraction of magmatic material. It can also indicate compaction of sediments or hydrothermal deposits. And, critically, it can reflect a redistribution of magmatic gases, CO2 and other volatiles, that are gradually released from the system. None of these processes, on their own, are catastrophic. They are the ongoing mechanical life of an active volcanic system. What researchers do is look at the combination, deformation data, seismicity, hydrothermal output, gas emissions, and groundwater chemistry to build a picture of what's actually changing. The 60-mile subsidence signal being discussed is consistent with what scientists describe as a hydrothermal-dominated deformation event, meaning the most likely driver is changes in the distribution of fluids beneath the surface rather than a direct signal of magma movement. But let's be precise about that, because the language matters. Here's the part that tends to get lost when headlines grab onto Yellowstone stories. Yellowstone's ground has been going up and down for as long as we've been measuring it, and the record, when you look at it carefully, shows a system that oscillates between periods of uplift and subsidence in ways that are far more dynamic than most people realize. Between roughly 2004 and 2010, Yellowstone experienced one of the most significant uplift episodes on record. The caldera floor rose by as much as 25 centimeters in certain areas. Researchers identified the likely cause as magmatic fluids migrating into the shallow crustal system. This was real, measurable, and genuinely studied. Then the system transitioned. Uplift slowed, and in various areas, reversed. What followed was a period of more complex, spatially variable behavior, some areas subsiding while others remained relatively stable. This oscillating pattern is actually what you'd expect from a system as hydrothermally active as Yellowstone. The superheated fluids that move through the fractured rock beneath the surface aren't static. They migrate, they phase change, meaning liquid water flashes to steam under pressure changes. They dissolve and reprecipitate minerals, and they respond to the slow tectonic and volcanic forces acting on the crust. What's interesting about the current subsidence signal is specifically the scale, that 60-mile footprint. Localized deformation events happen regularly and are largely unremarkable in the context of Yellowstone monitoring. When something covers a much broader geographic area, it suggests the subsurface process generating it has a correspondingly large spatial influence. That's what's prompting the closer look. There are a few competing explanations for what's generating this particular deformation pattern, and they're worth walking through because understanding them gives you a much more honest read on what this might mean. The leading interpretation among most researchers studying the data is that this episode of subsidence is driven primarily by changes in Yellowstone's hydrothermal reservoir system. Beneath Yellowstone, there are extensive zones of porous, fractured rock saturated with superheated brines, extremely hot, mineral-rich fluids that are under significant pressure. When conditions change, a pressure differential caused by seismic activity, a seasonal change in recharge from snowmelt, a shift in the thermal gradient, those fluids can redistribute. If they migrate away from a particular zone, the rock above that zone experiences a reduction in support. Combined with the natural elastic rebound of the crust, this can produce measurable subsidence. This is fundamentally different from a magmatic signal, though the two can interact, and distinguishing them requires careful analysis of the seismic data alongside the deformation data. A second possibility, which isn't mutually exclusive with the first, involves the behavior of the shallow magma reservoir itself. Yellowstone has a well-documented partially molten zone at depth, a large body of rock that's somewhere between 5% and 15% melt fraction, meaning it's mostly solid but has significant liquid magma dispersed through it. When magmatic gases, particularly CO2, gradually exsolve from this material and migrate upward and outward through the crust, the net volume of the reservoir decreases slightly. This can produce a subtle, broad subsidence signal at the surface. A third contributing factor that researchers consider is the long-term cooling of post-eruptive volcanic material. Much of the rock beneath Yellowstone is composed of material emplaced during the massive eruptions of the Yellowstone system's geologic past. The last major event was approximately 640,000 years ago. That material has been cooling ever since. As it cools, it contracts. That contraction is slow, but over large volumes of rock, it contributes to a background subsidence signal that can be detected by precise satellite measurements. The current 60-mile episode likely reflects a combination of these processes working together rather than any single clean cause. The scale of this event is genuinely what makes it stand out from routine deformation monitoring. To put 60 miles in perspective, the Yellowstone caldera itself, the collapsed volcanic structure at the center of the park, is roughly 34 miles long by 45 miles wide at its broadest extent. So the deformation zone being described exceeds the caldera boundary by a meaningful margin. It's spilling out into surrounding terrain. That geographic reach matters for a specific reason. The process is most likely to generate subsidence signals that broaden those operating at scale across the hydrothermal and upper crustal system, not those confined to a small, localized area. A single geyser basin draining or refilling doesn't move the needle over 60 miles. A broad reorganization of the subsurface fluid architecture can. What researchers look for in situations like this is coherence, whether the deformation pattern has a clear, interpretable shape. InSAR data, when processed carefully, can reveal concentric deformation rings, elongated troughs that follow fault systems, or asymmetric patterns that point toward a specific geometric source beneath the surface. Each of these shapes carries different implications for where the deforming source is located and what kind of process is driving it. The current event, from what's publicly available in the monitoring literature, appears to show a broad, relatively gentle bowl-shaped subsidence, consistent with a distributed source rather than a focused, sharp one. That morphology leans toward a large volume, diffuse process like hydrothermal fluid redistribution, rather than, say, a discrete intrusion of new magma. This is an important distinction that tends to get lost in the more dramatic versions of this story. The monitoring network around Yellowstone is extraordinary, and that's actually worth appreciating for a moment before I get into what the scientific community is tracking. The Yellowstone Volcano Observatory operates a network that includes more than 40 seismograph stations, dozens of GPS receivers that can detect ground movement in real time, continuous gas monitoring stations measuring CO2 and H2S emissions, stream gauges tracking hydrothermal water output, and the satellite-based InSAR program that's producing the data we've been discussing. No volcanic system in the United States is more closely watched. What the scientists tracking this current subsidence episode are particularly interested in is the correlation between the deformation data and two other datasets, seismicity and gas flux. On the seismicity side, Yellowstone generates thousands of small earthquakes every year, most of them too small to feel. And the spatial distribution of that seismicity can reveal where fluid or magma movement is occurring in the crust. If the subsidence zone correlates with a change in seismic activity patterns, that connection helps narrow down the most likely mechanism. On the gas flux side, the hydrothermal system at Yellowstone releases enormous quantities of CO2 annually. Estimates suggest on the order of 45,000 metric tons per day at peak output, which is a useful comparison point when evaluating whether the system's degassing rate is changing. If the current subsidence is associated with an increase in CO2 flux, that would support the interpretation that gases are exsolving from the magmatic system and migrating upward. If the gas output is stable or decreasing, the hydrothermal fluid redistribution explanation becomes more favored. The monitoring community has been clear in public communications that the current behavior, while interesting and worth tracking, does not represent an escalation toward eruptive activity. The criteria they use for concern, rapid uplift at rates significantly exceeding historical norms, shallow seismicity indicating new fracture propagation, major changes in thermal output, are not present in the current dataset. What is present is a large-scale surface expression of subsurface processes that are genuinely dynamic, genuinely important to understand, and genuinely underreported in their complexity by most of the coverage this topic generates. What I keep coming back to, after going deep on this, is how different the real picture is from what most people assume about this place. Yellowstone isn't a static bomb waiting to be detonated. It's an extraordinarily active, dynamic system that is constantly in motion, breathing in and out in cycles that play out over years and decades, shaped by processes ranging from the movement of deep magmatic fluids to the seasonal recharge of snowmelt percolating down through fractured rock. The ground sinking over 60 miles is a real thing. The satellites captured it. Researchers are studying it carefully. And it is almost certainly the fingerprint of a large-scale reorganization of the hydrothermal and upper crustal fluid system, which is exactly what you'd expect a system this active to be doing. But here's what I think is worth sitting with. The fact that we can detect this at all. That our satellite technology is sensitive enough to map millimeter-scale ground movement across a 60-mile zone from orbit. is, in itself, remarkable. We're in an era where the Earth's geology is becoming legible in ways it simply wasn't before. Every deformation episode, every seismic swarm, every gas flux measurement adds a data point to a growing record that helps researchers understand the difference between normal system behavior and genuine precursory activity. The more we learn the baseline, the better equipped we are to recognize when something actually departs from it. Yellowstone is going to keep doing what it does. The ground will sink. It will rise again. The geysers will keep erupting on their own strange schedules. The hotspot beneath it will keep pushing heat up through the crust. And the scientists watching it will keep publishing what they find, most of which is far more nuanced and far more interesting than any disaster film has ever managed to capture. If you want to keep following the real story on this, the one that's built from data, not speculation, I'll keep digging into it. Subscribe and hit the bell, because the next time a significant deformation event gets reported, you'll want the context to actually understand what you're reading. And if this is the kind of science that makes you see the ground under your feet differently, good. That's exactly what it should do.